I guess I'm a bit nervous because I was expecting a crowd of grad students, but I feel that I know quite a few of you, and so and you probably know much more than on many of the topics I'd like to discuss. And sorry, my face recognition. I keep it. So the topic is supposedly duality, and in fact, I did not select the title. Ben did, and in fact, when he invited me, he sent me this very nice email and inviting me to give a series of lectures. And he says on duality and its use in combinatorial optimization. And we hope you could speak about min-max characterizations, rounding, and the themes that unite basic ideas in LP to modern frontiers in TSP. Extremely well said. But then as I was preparing, I felt, oh, I should talk about this, I should talk about that, I should talk about this. And then I ended up having like 15 lectures or so. And then I said, oh, no, that's... So at the end, I was trying to focus on a few things. So I'm not going to cover all these. The plan is what I'd like to do is I'd like to illustrate some links between discrete and continuous optimizations. And I'll keep it at a very basic level. So I apologize for 3/4 of you, or maybe even 99% of you. Some of the themes that I will try to develop is the notion of a relaxation, how to go from a discrete optimization problem to a continuous problem. Duality is going to be also important, and I will start with some aspects of duality, but not so much from a discrete optimization point of view. First, I'll start from a continuous optimization point of view. And then I will also talk about rounding schemes in which you try to go from the continuous to a solution to a continuous optimization problem back to the discrete. Now, that's way too many things, so what I'm going to try to do is a random walk under the bridge, over the bridge, on the bridge, let's say. And so let me start with a few very basic things. So what's the beast of interest? The beast of interest is an optimization problem. And so we're trying to minimize some objective function, C of x, over x in S, over some set. And two cases that are of interest to us. One is the discrete setting, in which we could be optimizing over collections of sets. We could be optimizing over permutations. We could have a graph, and we could be interested in sets of vertices with certain properties on sets of edges with certain properties. And C is often linear. I mean, it's often a linear function of the elements in the set. So it could be, and then on the other side, we could also have S continuous. And in that case, what we would be interested in is we'd like to have some nice properties of S. So of continuity, differentiability. If we want to be able to efficiently solve this, we'd like S to be convex, for example. And or S could be, for example, a semi-algebraic set, and there will be some talks about this during the week. C of x would be often either convex or maybe a polynomial, maybe linear. So the one thing that's really very important will be the notion of a relaxation. And the reason that we're interested in relaxations is that many of the problems that arise in discrete optimization, like the traveling salesman problem, the stable set problem, and so on, are all hard to solve. I mean, most of them are hard to solve. And so we'd like to be able to transform them, relax them into easier problem. So instead of looking at minimizing Cx over x in S, what we'd like to do is we'd like to go to another problem, minimizing g of x, let's say over x in P, and we'd like to make sure that this gives us a, let's say, a lower bound on these values. So we'd like to impose this. And so one way to do it is, for example, if we assume that we are one optimizing over a larger set, so P contains S, and then also that that if I restrict my function g of x to the elements of x, then I get something that's, so I get c of x. So g of x is equal to c of x for all x in S. And so if that's the case, then clearly we have a lower bound. Now, some of the, so our goal is to have this problem to be easier to solve than this one. And then we'll be able to, we'll try to go back from the easier problem to the original problem. So among, maybe for now I should just off this.
You turned it off.
Okay, good. Thank you. So what are the properties, some basic properties of relaxations? Is that one of them is that if when we optimize over this problem, so if we let the optimum of g of x over x in P, if this solution, if x star belongs to S, then x star is also the minimum of the problem of interest to us. So the argmin over x in S of c of x. So, and how could we manage this? For example, if we succeed in having P to be the convex hull of S, then in that case, and for example, in the case in which c of x is linear, then we know in that case that we'll get an extreme point. The element that we're going to get in P will be also an element in S, and then we have equality in that case. So, but this idea is also very much used in cutting planes in integer programming, in which what you do is you'd like to optimize over a bunch of points. So ideally, you'd like to optimize over the convex hull of these points, but you may not know all the inequalities defining the convex hull. So what you might do is you might optimize over a larger polyhedral set that contains the convex hull. Then you optimize, you may get this point, and then you may try to find an inequality that's violated, like maybe this one, and you now optimize over this smaller polyhedron set, and you continue. You get, let's say, this optimum, and then you generate maybe this inequality, and now you can, by optimizing over this set, you would obtain this solution, which is a member of S, and so you get that the solution that you obtain is the optimum. So that's quite simple. Unfortunately, typically, it's hard to. Typically, we would take P not to be the convexal and have a P that's actually just it contains the convexal usually, but may not be equal. So what we could, but a nice property of a relaxation is that if we can somehow, by some heuristic method, find an element in S, so if find X in S of a certain value, or let's call it X hat, and then I also solve optimally this relaxed problem, and so let's say X star is the argmin over P of G of X. If that's the case, and then if I can relate the values, so if the value of X hat is not too much more than, let's say, alpha times the value of G of X star, then what's nice is that I know that then I know that C of X hat is at most alpha times the min over X in S of C of X. So that would give me a solution to my original problem that's approximately minimum. So very simple, very clear. Now, what if we have managed to define a relaxation that's easier? We can hope to be able to rely on duality. So duality is a nice way of taking an optimization problem that's so G of X over X in P, and creating a new problem, which is a maximization problem, H of X, H of Y, let's say Y in Q, in such a way that these two problems are related. In strong duality, you'd like to have equality between these problems. And the nice thing is that if you have a dual problem to your relaxation, then what you can do is, instead of finding the optimum solution to the relaxed problem, what you can do instead is only just, so if this min is at most the max or equal, then if you find an X in S and a Y in the dual of your relaxed problem, such that C of X is at most alpha times H of Y tilde, Y hat, then you again get the same kind of relation. So these are very basic things. I'd like now to talk a bit about duality. But I mean, even though I love min-max relations and duality in the discrete case, I first would like to go over duality in the continuous case. And I think then the right notion of duality for the connection between discrete and continuous optimization is the notion of conic duality. So suppose I have an optimization problem in which I have a cone K that's, I mean, we need some technical assumptions. We need the cone to be closed. It's a convex cone, so any line segment is within the cone. It's easier if the cone has non-empty interior. And I'm assuming that it lies, let's say, you could say on N, and you have the usual inner product, or you could even say you're in an inner product space and you have these inner product Cx. And you just have the cone constraints and then some linear constraints. So a typical case is, for example, linear programming, in which the cone is just the non-negative ortant, and then you impose that x belongs to the non-negative ortant, so it's non-negative, and you have these linear constraints, and you minimize. But then you can look at different kinds of cones and different kinds of optimization problem. So if you look at, for example, within the set of symmetric matrices, you look at the matrices that are positive semi-definite, and I'll define that in a second. Then you get the notion of semi-definite programming. These are two examples, but you could imagine even some completely combinatorial objects. So for example, you could look at the cut cone. And what is the cut cone is simply you take, in the cut cone, you take a graph on n vertices, let's say the complete graph on n vertices, and then for every set S of vertices, so the vertex set is the elements from 1 to n, you look at delta S, which are all the edges. So you have S, you have the complement of S, and you look at all the edges across. So delta S is the set of ij in the pairs ij such that ij intersect S as cardinality 1. And then you can look at the cone generated by the incidence vectors on these cuts. So you can define cut of n. It's just a set of non-negative linear combinations on these cuts as subset of n, such that lambda s is non-negative for all s. So I have my incidence vectors of all my cuts. I look at the cone generated by all these. So that could be my my cone, and then I would then optimize over a cone intersected by linear equalities. So no one calls that cut cone programming, but you could. You have the special second order cone, also known as ice cream cone, that also fits nicely. But then you can look at, for example, if you look at complex matrices, you can look at complex summation positive semi-definite matrices, and that would lead to complex semi-definite programming. Or in fact, I mean, my favorite one, and what you for people who will be here for a long time, they definitely need to talk to Jim and Pablo, who probably love this cone even more than I do. But so if I have time, I might discuss hyperbolic cones a bit. So now, how can we define duality for this cone programming? So the right notion is to look at this dual cone, and so we look at all the elements that have a non-negative inner product with all elements in K. And question is, what is that K star? So you can first easily see that the basic assumptions I had on the cone means that actually if I take the dual of the dual, I get the original cone. That's easy to see. It's also easy to see that if K is finitely generated, you have a finite number of elements that generate your cone, then you can easily say there should be greater or equal to 0. I'm not going to write on the screen, but this should be greater or equal to 0 for all I. And there should be a brace as well. And for example, if you take the non-negativity ortant, then you immediately see that that's equal to its dual, so it's self-dual. And in fact, there are quite a few cones that are the focus in continuous optimization that are self-dual. So the non-negativity ortant, the second order cone, the PSD cone, PSD over complex Hermitian matrices. So these are all self-dual. But in general, it's hard to get a handle of what is the dual. So for example, in the case of the cut cone, it's actually not easy to describe K star, because even though it's finitely generated and you know all the generators, these are all the cuts. The problem is that to get a description, the dual, you can get a description in terms of inequalities, but what's not obvious is what are the extreme ways of that cone.
Michel?
Yeah.
Is the definition making sense for any inner product or just for the standard inner product?
No, you can take any inner product. So yeah, so it's very, very general. So for example, in the case of positive semi-definite matrices, you can use the Frobenius inner product. And just a reminder, if linear algebra was a long time ago, so a matrix is positive semi-definite, a symmetric matrix is positive semi-definite if that quadratic form is non-negative, or equivalently you could say the eigenvalues are non-negative, or you could say that it can be factorized as V transpose V for some matrix V. So that's the Gram decomposition. Or you can express A in terms of a sum of non-negative rank 1 matrices. So the cone of positive semi-definite matrix, its extreme ways are rank 1 matrices. And the nice thing is that its dual is also the same cone of positive semi-definite matrices. Let's quickly see that. It's elementary, but let's quickly show that. So first of all, let me take an X which is in the pole, so it has to have a non-negative inner product with every Y. So in particular, it means that X times Y transpose is non-negative for every Y, but that means that Y transpose XY is non-negative, which means that X is positive semi-definite. So that implies X is PSD. Similarly, if X is PSD, then if X is PSD, then I know that X can be expressed, for example, as sum of lambda I, SI transpose, or VI transpose. These are the eigenvectors, and these are the non-negative eigenvalues. And so now, if I take X inner product with Y for any positive semi-definite Y, then I get that this is equal to the inner product of sum over I, YI, SI transpose times Y. And so this is this is greater or equal to 0 because this is the sum over I of lambda I times this quadratic form, which is now negative because Y is positive semi-definite. So that means that X also belongs to the. So it's self-dual, and so that's, if you look at that conic program, you get what's known as semi-definite programming. So you impose that your variables are the entries of a symmetric matrix, and you impose that matrix is positive semi-definite. You impose linear constraints, and you minimize or minimize a linear objective function. So one thing is that it's not minimized, but it's the infimum because the minimum is not necessarily attained. So as opposed to linear programming in which it's always attained. Now, this is the most important slide of the first part of this talk. So it's the duality over cones. So it's quite simple. So if I give you a conic program for some cone k, then you can write the dual in the following way. You look at, so this is a linear map, so you can look at the adjoint map, so such that this is satisfied. So that's also going to be a linear map, and you get that you'd like to impose that C minus this element is in the dual cone, and you'd like to find the supremum of this linear functional, and then the claim is that you get weak duality. So let's look at weak duality. Why is this at least that when X satisfies this and Y satisfies that? It's very simple. Z minus W is CX minus YB. So it's CX minus, for B, I can replace it by AX. And now I can rearrange it. I can say that this is A star Y times X. So that's C minus A star Y times X. And now, and that's the key, I have an element of K, an element of the dual, and so that's non-negative by definition. Now, in fact, for any cone, if you want to take the cut cone or if you anything, you always have strong duality. So you need some regularity assumption, and I can discuss that in a second. But under some assumption, you get that Z is equal to W. So the infimum here is equal to the supremum then, and they're attained. And so what is that regularity assumption? You can do it in several ways. One way is to assume that there exists. So remember, I assumed that K and K star were at a non-empty interior. So we can assume, if we assume that there exists a strictly feasible solution, so a solution in the interior of K that satisfies this, and also a solution Y that's in the interior of K star, then in that case you have strong duality. You always have weak duality, and you need this assumption, or you need something similar to have strong duality. Why is that enough to get strong duality? So strong duality is nothing complicated. So let's quickly argue it. So let's assume, for example, I have an interior. Let's for now assume just an interior dual feasible solution. So if I have an interior dual feasible solution, what I could do is I could look at so if I have a strictly so if I have a Y such that C minus A star Y hat, let's say, is in the interior of K star, what I can do is I can first look at the set of X in the primal such that its value is x in, so x satisfying the primal conditions, such that Cx is at most some value v. So one can easily show that this is assuming this is bounded. And this follows easily. I'm not sure I'll be able to do it on the blackboard, but we can try. Doesn't cost much to try, even when it's on video and being recorded, but that's okay. So, so what is Cx? Well, what is Cx? So maybe I'll look at my notes. Might be a better idea. So should I start it this way? If I can find my notes. So let me start from the dual. So I take that strictly integral solution, and let me take the inner product with x. So what is this? That's Cx minus this times that, and so I can rewrite that as y hat times a of x. But if x is feasible, so x in k and ax is equal to b. If x is feasible, this is b, so that's Cx minus y hat b. And so now that means that if I assume that Cx is at most v, I get that this is upper bounded by some number, and but this is in the interior of k star. So there is a small ball around it that's still within k star. So that means that x will be bounded. So the intersection with k will be bounded. So that means that, so if I look at the radius of a small ball, x will be in the radius of a ball that's inversely that times this. So x is, so this is bounded. So if it is bounded, the infimum is attained, and so that's a minimum. Now that you have a minimum, I feel so bad doing this in front of all these exponents, but that's okay. So if that's attained, then in terms of the supremum, you can easily use the separating hyperplane to show that you'd like to find a y that achieves the value of the optimum. So you'd like to get. So I told you that the primal is achieved. So that's the optimum value for the primal. And now I'd like to find a y such that yb is equal to Cx star. So for that, what I'm going to do is I'm going to try to, but again, what is yb? Yb is y times ax. And so this is y, this is a star y times x. And so I'd like to find a y such that this inner product is equal to that inner product. So what I'm going to do is to use my separating hyperplane result from convex analysis. What I'm going to look is I'm going to look at the space of A star y over all possible y's. And then I'd like that to be in C minus K star. So I have C minus K star. And if I can find a point that's in both, then I'm done. But if not, there exists a separating hyperplane, and that separating hyperplane has to be orthogonal to this space, so that I get a Z such that for every element in, so I get that Z, I have that C minus any element of K star times Z is strictly less than 0. Whatever I put here in K star. So that means that means two things. It means first that CZ is less than 0, and it also means that Z times K star is going to be, and I have also that Z times K star is going to be non-negative for all y in K star. But that means that Z is in K. So that's Z is in K, and CZ is less than 0, which means that if I take my optimum X star, and then from that optimum X star I go in the direction Z, I will stay feasible because this is linear and AZ is 0. So I'll stay feasible for the constraints. I'll stay in K because Z is in K, but I'm going to improve the objective function because CZ is less than 0, so it's unbounded. So that's the classical, I apologize for 99% of the audience, but that's the basic duality or convex optimization and specialized to cones. Okay, so let's go back to SDP for a second.
Michel,
yeah.
Before we do, could you go back 2 slides? So what happened? Oh, actually, no. I just wanted to see the example where the inf is not attained. That guy.
Okay. So you can, so if you don't have this,
yeah.
so if you don't have this, anything can break loose in the sense that the primal may not be attained, the dual may not be attained, and even worse than that, the infimum value might not be equal to the supremum value.
So if we go back to this one, I did copy it down right. So the problem with that one, so that has it, that satisfies Slater in the primal, but the dual ends up.
Right, exactly. So you'll have strong duality, but you will not, both the primal and the dual will not be attained. So only one of them. Now, so just to go back to SDP, so that's just the primal and the dual. So if you have a strictly feasible solution here and a strictly feasible solution there, then you have the inf is the min and the sup is the max, and you have equality. Now, one thing I'd like to insist, which is really cool, is the fact that at optimality, you have actually more than just. So at optimality, you know that at optimality, you know that Cx is equal to that, and when you rewrite that, it means that the x times s, and that's the slack matrix, that's a 0 inner product. Now, the nice thing about these cones is that this actually implies a much stronger condition. So just having a 0 inner product implies that actually the usual matrix product of x and s that's the 0 matrix. And so so that's are used to that. I mean, if you're on the discrete side, you are used to that for linear programming, but it actually carries through to more general optimization, convex optimization problems. So in linear programming, when you have the slack times your primal solution is 0, and both are non-negative, then you immediately imply that each component xi, si is 0. Same thing here, and again, it's obvious. So I like to do easy proof so that it's so let's see why this implies that. So suppose I have s times x is equal to 0. So what do I know? I know that s is positive semi-definite and x is positive semi-definite. Let's take first s positive semi-definite, so I can decompose it into, let's say, sum of lambda I si transpose, and so times x, lambda I are non-negative, and I are non-negative, so this is equal to the sum over I, lambda I, which are non-negative, times si transpose times x, but x is positive semi-definite, so let me instead write it as v times v transpose. So what is this? That is the same thing as SIV SI transpose V, V transpose SI. And so, so this is the square of this guy. So this is the same thing as that squared. And so I get that this is equal to the sum over I of lambda I times this. But this is non-negative and this is non-negative. So all of them have to be 0. So that means that in particular V transpose SI is equal to 0 for every I. But if this is true, then you get that VV transpose SI is equal to 0. And so that means XSI is equal to 0. But if XSI is equal to 0, it means that when I take the regular product of S times X, which is equal to the sum over I of lambda I SI transpose times X, this is equal to, since these will be 0, I get 0. So very simple. It's not doing, I mean, these are just for the purely discrete people that have not played with this in decades. So now let me switch gears a bit, and let me go back to the discrete. And remember what I told you. So here is a prototypical discrete optimization problem. You are given a graph, and you say that a set of vertices is stable or independent if between any pairs of them there is no edge. And the basic question is, what's the largest number of such a stable set? And that's denoted by alpha g. Now, alpha is known to be NP-hard, and there are also some strong results about inapproximability of alpha. But then there was an amazing result by Lova. So I would say that if you want to leave from here and take some take-home message, first you should talk to, first message was you should talk to Pablo and Jim about hyperbolic optimization. And read, for example, Jim's paper on it. And the second thing is you should go and read Lova's and maybe that's even before, I'm sorry, apologies to Jim and Pablo, but you should go and read LOVA 79. It's an amazing paper. And it's, so what he did was that he defined an upper bound. So in this case, we're maximizing. So when we relax, we'd like to get an upper bound on the optimum. So he defined an upper bound theta that has many different ways of being formulated. So can be stated as an eigenvalue bound, as a semi-definite program in terms of orthonormal representations and so on. Let me discuss one of the many semi-definite programming formulation. So when I told you initially, well, you'd like, when you look at the relaxation, you optimize over S and you optimize over P, and I said you'd like P to contain S. Well, in fact, I mean, what you really want is you want a map. You want a map from S to P, and then you'd like to make sure that if I evaluate the value of pi of x, this is C of x for any x in S. So in this case, what I'd like to take any stable set, map it to, so if I'd like to get a semi-definite program, I'd like to map it to a matrix that's positive semi-definite, and look at the properties of that matrix, and then I'm going to take a Largent space that contains all of these. So in this case, one of the many maps that are possible is to take a stable set and then map it to the following matrix, in which the matrix, if this is S, so what you would do is you would put 0 all over the place. And here you would take a matrix that's 1 over S times the matrix of all ones. So that's 1 over S times a matrix of all ones here. And so if you do that, notice some of the linear constraints that X has to satisfy. So one of them is that if you look at the trace of that matrix, the trace of that matrix is equal to 1 all the time. I divide it by 1 over the cardinality of S, so that's always equal to 1. That matrix, since it's a rank 1 matrix, but it's a rank 1 matrix with a non-negative coefficient, so that's positive semi-definite. Now, since I know that I don't have two vertices connected by an edge within S, so that means that actually I get that Xij is 0 if Ij is an edge. And then if I want to see what is the size of my S, so I'd like to compute C of x. So what I can do is I can just look at my matrix X and multiply it by a matrix of all ones. Take the product with a matrix of all ones, and that will be my cardinality of S. So my map in terms of values, I will evaluate the value of a positive semi-definite matrix in terms of this inner product. Now all this is nice. That's a conic program over the positive semi-definite matrices, except for this one. So if I want to keep this, I would then have a bijection between S and P, and I would not lose anything. But since I have to relax this if I'd like to get a nice conic program over positive semi-definite matrices, I will get an upper bound on alpha, and that's given by this semi-definite program in which I have the semi-definite programming constraints plus the trace the trace and these. Okay? Now, now, what's amazing about these theta function is that if you look at a subclass of graphs, so the class of perfect graphs, and what's the notion of a class of perfect graph is that if I look at the largest stable set, so clearly a stable set and a clique. So a clique is a complete subgraph. A stable set and a clique can have at most one vertex in common. So if I have a stable set S, and then I have a bunch of cliques that cover all the vertices of my graph, then each clique can contain at most one vertex of my stable set. So this is a clique, that's a clique, that's a clique. But each clique I use can contain at most one vertex of my stable set. And so the number of the smallest number of cliques covering all the vertices, that's an upper bound on the stable set number. So for any graph you have that alpha So for any graph, for every G, you have that alpha of G is at most these smallest number of cliques covering all vertices. Now, you define a graph to be perfect if not only this is true, you have equality, but it's true also for every subgraph. So for every subgraph of, if I look at the induced subgraph G of S, this must be equal to the clique covering number. So there are lots of nice classes of graphs which are perfect. For example, you can take bipartite graphs, cordon graphs, and so on. An only nice result of Lovaas was to show that if you have a graph that's perfect, its complement is also perfect. And its proof is a purely polyhedral proof. So it's really a proof that goes into the continuous setting. In fact, I should do that. I'll do that after the break then, after the eclipse. Now, this really long-standing open problem, which was resolved by Chudnovsky, Robertson, and Simon, is actually is a characterization of the graphs which are perfect. So the graphs are perfect if and only if it has no cycle of odd length with no chords, and similarly no complement of that.
Also Robin Thomas. Sorry.
And I'm sorry, yes, definitely. Chudnovsky, Robertson, Simon, and Thomas. Thank you. Apologies. That's the problem when you do the slides at the last minute. Now, the amazing result of Lovaas as well is the fact that for perfect graph, you have equality between alpha of G and theta of G. So you can compute the largest stable set in a graph by solving these semi-definite programs. So that's, as Ben was saying, there is no gap between discrete and continuous optimization. So that's the nicest example of, in my mind, of really using continuous optimization for solving a deep question in discrete optimization. So the largest stable set can be found efficiently using SDP. And
there was no combinatorial algorithm there.
So there was no, yes. So so in fact, yeah. So that's so in terms of the history. So in 1979, Lovaas published this amazing paper that has, it's only 7 pages, but just describing all the results in it would take probably 5 lectures. So, and so that's, but at that time, semi-definite programming was essentially inexistent. So in that 7-page paper, he developed duality, he developed everything about semi-definite programming. In fact, it's very much between the lines, so, but it's very nicely done. And, but then there was no algorithms for it. But then it was, then the ellipsoid algorithm came out, or at least it came out in the West. And Groce, Lovaas, and Scrivon noticed that you can actually solve this in polynomial time up to an epsilon, and since in the case of perfect graph you have equality, you know that this will take only integer values from perfect graphs, and so you can actually go from weak optimization to strong optimization. So the fact that you can compute this in polynomial time was first known when the ellipsoid algorithm came out, and its applications in discrete optimization were observed. Later, when the strong perfect graph theorem was proved by Chudnovsky, Robertson, Seymour, and Thomas, there was actually an algorithm for optimizing over it did not come with it. So one needed to do more work, and there was a subsequent paper with a slightly different set of authors that shows that you can also use this decomposition to do it efficiently. Now, one thing I'd like to mention to connect to just in the 1 minute that remains before we go see the eclipse is the following, is that if you look at, let me define 3 polytopes or convex sets. In fact, two polytopes and 1 convex set. So the first polytope is the convex hull of all stable sets in the graph. And then you could say, well, I know that a clique intersects a stable set in at most 1 vertex. So I could just look at these inequalities, and that's another polytope, but it's a larger polytope than the stable set. That's not enough to describe the stability. So Q stab of G is a superset of stab of G, but you don't have equality, typically. And then you can put something in between that's motivated by this work of Lovaas, and that's this semi-definite program. So you have a semi-definite program defined on the matrix Y, and it's a matrix that's n plus 1 rows by n plus 1 if n is the size of the vertex set. And then you read from the first row, you read the entries x sub i's, and that's going to be an element that's in Q stab. It's sandwiched between stab and Q stab. So that's what Don Knuth called the sandwich theorem. Now, what's very nice is that in the case when the graph is perfect, you have actually equality everywhere in these inclusions. So the stable set polytope is equal to the theta body, which is equal to Q stab of G. And this is actually only true for perfect graphs. So that's a characterization of perfect graph. G is perfect if and only if you have equality here. And similarly, this theta body, which is this semi-definite program, is going to be polyhedral if and only if G is perfect. And one thing I would love to see is actually being able to check, to decide if a graph is perfect by doing it polyhedrally on proving or disproving that TH of G is polyhedral. Now, the final thing I'd like to say is that this is a unique example of a polytope, namely the stable set polytope, which we were able, not we, Lovaas and company were able to lift to a higher dimensional space, have define a one of these spectral agents, so one of these semi-definite constraints, and then projecting it down and get exactly that polyhedron set. So it's hard to visualize, because you would imagine that if you take something that's actually round and then you project it, kind of, you would assume it's not polyhedron. But so that's an amazing example of, you'll see talks about extended formulations later in the week, and so this is an amazing such example. So let me stop here, and we'll continue after the eclipse.
Maybe one quick question before we go for the eclipse. There are any?
You can ask the question, and then I'll respond after the eclipse.
Yeah,